So let's continue in Lumerical Charge for optical modulator. So as you see here in this part, we have material, geometry, simulation region, and charge. So for the material, so similar to the Lumerical mode, we can add our material from here, electrical and thermal property. For instance, if I select a gallium arsenide, you can see we can put electronic property and thermal property. And in the electronic property, we can put the material characteristic like permittivity, work function, or gamma value here. And then also for the fundamental part, you can see we have effective mass, and our effective mass depends on a temperature. It means that the temperature simulation, the temperature characteristics is included in the Lumerical Charge. And so for the band gap also, you can see that the EG, our EG is 1.42, and this is dependency of band gap to the temperature. So, and for the recombination, you can see a different recombination like shotcrete holes, Auger, radiation, and ionization, band to band. And here we have selected shotcrete hole, Auger, and radiative. And yeah, you can visualize the different parameters as you wish. For instance, you can put visualize, and also in the thermal property, you can put the thermal characteristic like density specific heat and other parameters here. And also you can visualize a characteristic of material like this one, visualize. And for instance, I want to visualize the EG, so I will select the EG and then create a visualization. And this is how my visualization curve. So let's, and then we can create, and we can select a color for the material, and then can come back to the material parts, because I generated my material here. So I click cancel, and you can see a different material here: aluminum, gallium arsenide, aluminum. And you see for each material we have a optical characteristic and thermal characteristic. So this is a general introduction of material. And for the geometry, this is our geometry. So before I describe the geometry, let's I can describe charge part in more detail. So in the charge part, we have a solver. In the solver, we can insert the mesh characteristic and our solver type, because our solver type is charge. So we can insert any doping that we want. And this is our boundary condition. For instance, if we want to connect our device to the metal, for instance, the power supply, we need electrical contact, or other boundary condition that you can see here. We can have a different source, optical heat, delta temperature, and these sources can be imported from the other softwares also. These are our monitors: charge, electric, band diagram, current, temperature, and this is our simulation. This is the brief introduction of the taskbar. And so let's continue to the geometry. This is our geometry, and this is our geometry. So our geometry is similar to the Lumerical mode that I described in my previous session. So the previous part, you can follow my previous part. So this is our anode. This is gallium arsenide type of top, a super lattice. And this is our multi-quantum well. I go to the multi-quantum well in more detail. So this is superlattice, you can see color, and this is gallium arsenide top and substrate. And this is our cathode. So this is our cathode, this is our anode. So we want now, actually, these are used for our contacts because we want to connect the power supply to our device. So for instance, our anode is aluminum, and you can also right click on the anode and you can select edit object, and you see its material is aluminum, and this is a geometry. So and this is our gallium arsenide. Superlattice is aluminum gallium arsenide. You can see here. So yes, all of our superlattice are gallium arsenide. You see here, and also you can select edit object. You can go to the material and see the aluminum gallium arsenide is our material. So now regarding to the multi-quantum well, if I zoom it well, we have 3 barrier. So these are 3 barrier, and we have 2 well. Our barrier is aluminum gallium arsenide, and our well is gallium arsenide. So our well is 9.4 nanometer height, and our barrier height is 200 nanometers. Yes, this is barrier 1, and barrier 2, 200 nanometers, and barrier 3. So this is general structure. So let's continue in the simulation region. So this is our simulation box. You can see here, this is our simulation box. Is 2D y normal. This is Z, this is X. So this is 2D y normal. So you should take care that our simulation box must cover a part of metal anode and cathode and all of the structure. So let's right click on the simulation parts, edit object. You can see that our simulation is 2D y normal. X and Z boundary condition are closed. Our material, the background material is known because we define all of the region of our simulation part is defined, so we don't need to define any material, and this is our geometry. And also to insert a file from Lumerical mode to the Lumerical charge. If I right click on the model and click edit object, you can see I define some variable. This is the variable that quantum confinement Stark effect, that this file, the file name that I've generated in Lumerical mode, and this is the script. It's very easy. You can by this script you can load the ineffective part of our file to the real ineffective variable. So you can also put the select test and it works. So let's review the charge part. So in the charge part, you have different parts, the boundary condition, some constant doping parts, meshing part, and some monitors. So let's regarding to the boundary condition. It's very easy for the boundary condition. We have because we want to connect our metal anode and cathode to the voltage. So our cathode voltage is constant, but our anode voltage is different, as I described in my theoretical part. So let's select anode, and you can bring the anode from here. You can see here. Easily you can add any condition that you need. So if I right click on the anode and select edit object, you can see that our boundary condition mode is steady state because our voltage is constant. So the sweep type, I select the value and put the value of sweep type here. We change from 0 to minus 0.5, minus 1, minus 1.5 to minus 10.25. So our force ohmic also is true. So the geometry, our geometry is solid, and I select the solid as anode. So it's very important to select anode. So if I scroll down, you can see a different solids here, but for the anode, we select anode here. Then, and also for the cathode, the same thing as anode, but the difference that the sweep type is single because our cathode voltage is 0, and also the geometry will select the surface domain as solid and solid as cathode. So next, we need to see the doping part. For the doping part, we can select the partition from the charge. If I select partitions, so, and then if I select the doping, you can see a different doping part, the constant doping region. So the green box, as you see here, this is a N, this is P, and this is P++. For the N, if I right click on N and select edit object, we can see that our doping type is N, concentration is 1E18. So, and also for the P, the same thing, but please look at the green box, and we can see that our P is 1E also 18, and this is our P++ region. So the boundary between the anode and gallium arsenide top. So it's 1E 19. So because we need to have a contact. So next, because if you look at the simulation region, actually, sorry, for the charge, if you look at the mesh setting, you can see that our mesh edge length is around 10 nanometer. So now we want to increase the accuracy for the multi-quantum well part here. So we can import this mesh quality constraint from here, you can see. And if I select the mesh quality, you can see that our mesh maximum mesh region length is 2.5 nanometers. So because we want to increase our accuracy in the multi-quantum well region. So now we want to add some monitors. So I actually added 3 monitors here: band structure monitor, field monitor, and charge monitor. For the band structure monitor, I want to, so if you look at the monitor, you can see that our monitor is the linear Z, just it's on the Z direction. I want to record EC, EV, EI, EFN, and EFP. And I will show you the result of band structure, and you can see that these parameters. And also for the field, I want to record electric field, and for the charge, I want to record electrons and holes. So how we can insert the monitor, you can insert the monitor from here, charge, electric field, and band, like this. You can see that our band is added, and you can select the different monitor type that you want. So I manipulate this. So now I think everything is ready to simulate, but I simulate this file before. I want to show the results. So let's start with band structure. So if you remember our band structure, so this is N-type, this is P-type, and this is P++. And our Z started here to here. And so let's go to see the band structure. So if I select the band structure and then select the visualize band structure, yeah, you can see the band structure here. So you can see that we have EC, EV, EI, EFN, and EFP. So this is our EC, this is our EI, this is our EV and EFN and EFP. So let's remove the, for instance, EFP and EI to discuss better way. And I put the EFN as I can select a marker for EFN, for instance. This is for our EFN. And marker size, maybe it's good. So this is our EFN. So let's, here are gallium arsenide in this region. This is our in-gas, indium gallium arsenide, superlattice. And also this is in-gas. This is our quantum well. We have two quantum well. Our quantum well is gas. This is in-gas. And again, this is in-gas, and this is gas, but P-type. So this is P-type. You can see here, this is our N. This is our P-type. And here is our N-type. So it's clear. Now, I can load in a new window. So now if I change the anode voltage from, for instance, here is 0 volt, I can change the anode voltage to, for instance, you can see if I increase the voltage, reverse bias voltage, you can see that our band diagram is tilted more. And for instance, for -5 volt, you can see that you can compare the results two curve here. You see, this is for 0 volt, and this is for -5 volt. You can easily see that our band diagram is tilted. So this is the study of our band structure. So let's, and also I described the principle of is why our band structure is tilted when we our semiconductor to the reverse bias voltage. So next, let's close this windows. So I want to show you multi-quantum well absorption. So if I select the charge and also I forgot to to show you the quantum well part. So if you select a charge and edit object, select edit object, you can see our simulation region is simulation region, and our solver mode is steady state. We want to, our temperature dependence is isothermal, but be careful about this one. Multi-quantum well is multi-quantum well layer. So I described the mesh setting before. We don't have any transition or small signal here. We want to record all of these parameters. And in the multi-quantum well part, you can add your multi-quantum well here, you know. Layer 1 is 200 nanometer, is super lattice. So we add 3 barriers, so 1, 2, 3 barrier, and 2 well. Our well was 9.4 nanometers, so, and our barrier thickness was 200 nanometers. Yes, because I forgot to describe this one. So let's come back to the charge part, and I select multi-quantum well emission. So if I select multi-quantum well emission and I select the visualization, you can see that I select the line and then select frequency as plot X, so you can see and change the unit to terahertz. So you can see and also show the legend. So you can see for the absorption for the TE and absorption for TM. So as you see here, for the T, we have a 2 excitonic peak, as I described here, and I showed in my presentation. You see here for the absorption part, we have 2 peaks for the excitonic peak, and so let's also change the wave, the access to wavelengths to compare in a better way. So if I select frequency to wavelengths, you can see that, and also micrometer, select the wavelengths as a micrometer. So now you can compare it in a better way. So we have a 2 excitonic peak here. So now if I remove the TM and just focus on TE, you can see that. And if I change the voltage value from 0 volt to higher reverse bias voltage, you can see that easily. So let's take a picture of this value and then change the voltage value. You can see that when we change our voltage, easily we can see our red shifted. And for instance, for -10. And if I compare these 2 pictures together, you can see that easily our curve is shifted. For instance, this is our first excitonic peak. Our first excitonic peak shifted to the larger wavelengths. For this reason, we named actually quantum confined, the star effect. Actually, we have a red shifted in the wavelengths. So yeah, that's the absorption part. And for the plot the and plot the index also, multi-quantum well index. If I select visualization, new visualization, and again a similar thing, line, and then Gauss legend, and if I select frequency as plot X, select wavelengths, this is our index, real index, and for T and TM, if I remove the T part and just focus to the TM, TE, so you see that this is a real refractive index. And if I select the imaginary part, you can see that this is our imaginary part. And imaginary part is a similar behavior absorption, because yeah, you can see that they have a 2 excitonic peak as I described in a absorption part. And also we can see the same thing. If I change the voltage, we can see a redshifted in the plot. So now we can also plot the field, electrostatic fields. So this is our electrostatic fields, and also if I change the voltage, we can see that our electrostatic field is increased. So let's plot this result in the script also. You can also do these curves with a script. So you can load the file from Lumerical mode, and this is our active region length is 150 micrometer. I want to plot for this 3 voltage value. So let's read the anode voltage and save it in the bias and find the index of bias. And let's read the multi-quantum well emission from the charge part that I've showed you, and also multi-quantum well index from the charge, and save the results in absorption T, absorption TM, index T, and index TM, and read the frequency and wavelengths and energy. Then we can read our electrostatic field that I've showed you from charge field character electrostatic part. And for the number of layer, for number of well, we have a 2 well, so then we can calculate the E field based on kilovolt per centimeter, and we can plot the results. So in the results bar, I want to plot absorption TE versus EN, and energy and absorption T versus wavelengths. And also I'm interested to calculate the transmission by this formula. As you see here, we have so our transmission is calculated by this formula actually. Exponential this formula. So they put instead of omega 2pf. So let's 2pf, 2pi frequency, and the real. So let's again. So this ineffective value comes from Lumerical mode, confinement factor from the Lumerical mode. We define the L, and this delta N quantum well calculated in Lumerical charge. So so you can see here, this is a real and effective that I showed you on the model, that we saved the ineffective result of Lumerical mode in this variable. And also you can see here again, you come to the variable, you can see that we save the file to the real and effective value. So so this is our confinement factor and our active region length. So be careful that, because we work on a structure quantum well, and our gas has a larger refractive index. So for this reason, we have optical confinement, and our active region length is 150 micrometers. It's very good for this case. So next, we can plot the transmission versus energy and transmission versus wavelengths. So this is our group delay calculation. And then we export the result to Lumerical interconnect by multi-quantum well output. So multi-quantum well, so we save the energy, bias, absorption, and group delay. So, and then we save the files to electro-absorption spectrum data.txt. So now everything is ready. So let's run the simulation. If I run the simulation, we have a transmission versus wavelengths, and we have a transmission versus energy and absorption versus wavelengths and absorption versus energy. So now, yeah, you can see there when we increase the reverse bias voltage, we have a redshifted as I described before. Let's focus on this plot. So as you remember from my slides here, for the designing of electro-absorption modulator, for instance, we can focus on excitonic peaks. So this is our excitonic peaks. So as you see here, the blue one shows the case that our voltage is 0. So our excitonic peaks is in 0.851932 micrometer. So but for this case, minus 5.5 volt. So our excitonic peaks is disappeared. So we can use this characteristic to design our electro-absorption modulator. Or for the other case, for instance, of quantum well and graph, and you can see that when we put the voltage, we can see that we have a redshifted in the curve. So for this reason also we can use this characteristic for the electro-absorption modulator design. For instance, here in this wavelength, you can see in this wavelength, for the case of 0 voltage, relative to the case of minus 10.25, we have different absorption parameters, and we can use this characteristic to design large modulator. So let's summarize the results. So you learned how to define a material, how to define your geometry and simulation region, and the boundary condition, and different doping parts, and insert monitors, and also scripting. You can write your script here and read the data from different monitors, and you can analyze and electro-absorption modulator, and you learn how to define a multi-quantum well configuration and layers. So you can see that the multi-quantum well definition. So I think we covered everything, and if you have other question, you can send me an email, and I will answer your question. Thank you very much. So let's